Okay, here we go with the double and half angle identities. This is going to be the last group of identities that we cover in this section of the class. And before we utilize these, I'd like to just quickly establish each of these rules. Now we do have a what we call a double angle identity for sine that's provided to us here in this chart, and we've got three different forms of the double angle identity for cosine, and that's because, well, these different forms might benefit us differently in a variety of situations. So we'll see why we might use three of those here in a little bit. But why do these double angle identities work? Where do they come from? Well, we can very quickly establish them over here. So let's start with this sine double angle identity. So we're sort of saying that sine of 2 theta, sine of 2 times some angle measure. Well, another way we can write that is to say that sine of theta plus theta is the same thing. Because, of course, sine of 2 theta is the same as sine of theta plus theta. And now this looks like a sum identity for sine. We just talked about those at the end of last week. So here we can use our sum identity rule. And the sum identity said, especially if we consider this alpha and this beta, the sum identity said that sine of alpha, which in this case is represented by the letter theta, times cosine theta plus cosine theta times sine theta. And here again, what I'm using is the sum and difference identities from last week. So with sine of alpha plus beta, we said we would take sine of alpha times cosine of beta and add that with cosine of alpha times sine of beta. And in the instance of today, both alpha and beta are represented by the letter theta, so we can write them this way with theta. And of course, sine theta times cosine theta is the same as cosine theta sine theta. So we could write those together and combine like terms to cosine theta sine theta. You could also write it as 2 sine theta cosine theta, as was given in our handout today. You may notice these little squares drawn at the end of a series of statements. That's kind of an indicator that our proof is finished, that we've completed completed the establishment of the identity. This is just a carryover of what I used to have to do in my undergraduate work. So if you see me writing these blocks at the end, that's all that means. It's just an indicator that we're done. Let's try the double angle for cosine. Let's see if we can establish this one or two different ways. Here again, I'm going to say that cosine of 2 theta, cosine of double an angle measure, is the same as cosine of theta plus theta. And again, if I'm using my sum or difference identities, well, here's cosine of alpha plus beta, so that's cosine of the first angle times cosine of the second angle, minus sine of the first angle times sine of the second angle. Well, both of the angles are the same, so this looks to me like we have cosine of theta times cosine of theta minus sine theta times sine theta. And cosine theta times cosine theta is cosine squared of theta. And sine theta times sine theta is sine squared of theta. And I didn't do this with my last example, but again, we're establishing these identities, and 2 sine cosine theta, yep, that checked for sine of 2 theta, and yep, cosine squared theta minus sine squared theta, that's what we've got here. Well, what about this second and the third form of cosine 2 theta? How do we get that? Well, for that, I think we see these cosine squareds and sine squared. So if it were me, I would start considering our Pythagorean identities. If you recall, sine squared plus cosine squared is equal to 1. So cosine squared by itself is 1 minus sine squared, but also we could get sine squared by itself and say that sine squared theta is equal to 1 minus cosine squared theta. So with these two pieces of side notes, let's see what happens if we make a substitution. So for identity number 3 here, let's replace this cosine with 1 minus sine squared. So for number 3, we could say that cosine of 2 theta is not equal to cosine squared minus sine squared, but we'll say that it's equal to 1 minus sine squared minus sine squared. And again, we're writing this in place of cosine squared. And we've got two like terms, and we can also clear the parentheses here. So we've got 1 minus 2 sine squared theta. That matches our third identity for today. And in a similar fashion, our fourth identity can be established too. Let's take a quick look at that. So cosine 2 theta, if we replace our sine squared instead, so we've got cosine squared minus 1 minus cosine squared. This one's a little bit tricky because when we distribute this minus sign, changes the signs of both of these. So in fact, we're adding cosine squared. And cosine squared plus another cosine squared is 2 cosine squared with this minus 1 left over. And that proves or establishes our fourth identity. And again, we'll use the right side of these equations. We'll use these as needed on the right side to ever rewrite an expression that looks like those on the left. Should there be a need in a larger equation to rewrite and or simplify, we now have some additional techniques to do so. The establishment of the tangent double angle identity is shown here, so I'd like for you to read through this and think about it on your own for just a moment. If we know the sum identity for tangent, and we let alpha and beta be the same thing, we'll call them theta, what would the final form of the double angle of tangent look like after we've written the sum identity as the sum of two identical angles? What would the simplified result look like? Go ahead and pause the video now. Think about that. Try to establish this and resume playback in a moment to check your answer. And here we have it. In the numerator, tangent theta plus tangent of theta is the same as 2 tangent theta. And in the denominator, 1 minus tangent theta times tangent theta is 1 minus tangent squared of theta. So our double angle identity for tangent looks something like this.